This is a relatively long report, so I'm going to just give it a brief summary, but it's from the International Carbon Partnership, Carbon Action Partnership, which looks at emissions trading systems and carbon capture and storage, considers various design aspects, their interactions between the emissions trading system and carbon capture and storage, and what are the various issues one has to worry about. So it's basically mapping possible interactions, technical considerations, and existing provisions of the emissions trading systems and carbon capture and storage. I won't read all the details from the main summary. I've taken the text that we'll just read the headlines of. We already discussed carbon capture and storage applications in various different podcasts, so we will just see again that fossil fuel energy and industrial point source capture with storage is possible, and it's easier than, let's say, taking it out of the air, because direct air capture means you're only got 0.04% of carbon dioxide concentration in the air, so taking it out is enormously challenging in terms of energy requirements and just in terms of scaling it up. Lot of flow through will be required. So concentration from point sources will be medium to high, and then you can do a geologic storage, or technically you can also convert it into biomass and convert it into bioenergy with carbon capture and storage, waste to energy with carbon capture and storage, and so on. And direct air capture and storage is very much a player. Various implementations have been done already, but none of them shows yet the promise of scalability required to reach our net zero targets, decarbonization goals, etc. So this is the executive summary. The interaction between emissions trading systems and carbon capture and storage applications is likely to become an ever more relevant topic of regulatory attention. The basic idea is to think about how ETSs could interact with CCS applications and the attendant opportunities and risks. The challenges faced when designing ETS regulation related to carbon capture and sequestration, whether ETS doesn't consider CCS as emissions not put out, or if it interacts with CCS in some way, and then whether it considers a technological removal of ETS as emissions taken out, and so on and so forth. The specifics of how different ETSs implemented to date interact with CCS applications have to be looked at as well. So the key context in the background here is that CCS applications capture and geologically store carbon dioxide. This is the goal, and that's what everybody is fighting for in terms of efficiency, design, reducing cost, making the CCS systems themselves net zero in a life cycle sense, and so on. Fossil energy and industrial point source capture is what is quite easy to accomplish, and these emission sources are typically covered by ETSs as of now. Technological or CCS based removals, of course, are where the previously emitted CO2 from the atmosphere is somehow removed, like BECCS, bioenergy, carbon capture and sequestration, waste to energy with CCS, and so on. These activities right now are typically not covered by ETSs. So the question is, going into the future, how ETS and CCS are going to interact. CCS can be an important element in the decarbonization pathways of sectors covered by ETSs. This is always considered in the scenarios that typically the International Energy Agency puts out for net zero by 2050 and so on. Several new CCS projects are under development, but there remains a large gap between their potential capacity and projected decarbonization pathways. If we keep our global warming targets in mind and we look at CCS, which by now is obvious will be a part of the portfolio of accomplishing net zero and decarbonization, even in all the IPCC scenarios. And there is a lot of debate. I have a podcast on how the IPCC scenarios of when we will hit net zero, or when we will need to hit net zero to meet the global warming targets, are reliant on technological promises that are not guaranteed to be fulfilled in terms of technologies to accomplish these goals. So looking at that a little bit here, global energy sector CO2 emissions reductions by measure in the sustainable development scenario relative to the stated policy scenario 2019 to 2070. So we know where we need to be for a sustainable development scenario, but if you watch carefully the stated policy scenarios as of today, they are obviously not on the same path as sustainable development scenario. So one can look at the differences in terms of gigaton CO2 per year needed to meet those gaps between the two. So here is the avoided demand, so actually reducing consumption, technological performance by 2070, electrification, hydrogen, how that is going to contribute, even though this is still a technological promise, because you can see even out to 2030 it doesn't have much of a role to play. And bioenergy, again, it's not clear how it interacts with food security, water demand, and water quality, air quality impacts, etc. Other renewables, other fuel shifts, and here is CCUS, and you can see that CCUS will continue to play a larger and larger role out to 2070 in terms of sustainable development scenario. And if you look at where we are now, especially in terms of the world CO2 emissions reductions from CCS and CCU, so carbon capture and storage, carbon capture and utilization by technology readiness category in the IEA sustainable development scenario relative again to the stated policy scenario. Current mature technologies for carbon capture and storage or CCU only will contribute 2% by 2070, which means the rest of the drawdown is going to have to come from early adoption of 35%, those technologies that are in a demonstration phase by 50% by 2070, and those that are prototyped right now are only going to contribute about 13%. So this is what we mean by technological promises that are yet to be fulfilled in terms of actually hitting our targets through CCS as a part of the overall solution of decarbonization and net zero. Carbon capture cost curve in US dollars per ton of CO2 equivalent. So we convert non-CO2 greenhouse gases to CO2 using the global warming potential calculation. So that's in 2020, and abatement potential in gigaton CO2 equivalent. Here, looking at cost per ton of CO2 sequestered in US dollars per ton of CO2, you're looking at the scale here, looking at low-cost reforestation and agroforestry. So this is the carbon capture potential. So they have low cost but low potential. And you have natural gas processing with CCS, medium cost forestry with agroforestry, for example. So that has somewhat higher potential for CO2 sequestration. So these fall under natural sinks, occupying the lowest end of the sequestration cost curve, but their potential is also on the lower end of the scale. So this is the fertilizer and chemicals production with CCS, high cost forestry again with agroforestry included in the natural sinks we are considering. Industrial CCUS considers iron and steel CCS, coal power plant CCS, IGCC. So this is the various processes from NGCC, IGCC, cement, bioenergy, and CCS. So direct air capture is up here with very high cost and also very high potential for drawing down CO2. So direct air carbon capture and storage, the wild card technology that could unlock almost infinitely scalable decarbonization potential. But this also means that this can be interpreted as saying we can continue with our lifestyles without reducing CO2 and without reducing fossil fuel reliance, and simply keep drawing down CO2 from the air. This is a double-edged sword that one has to be very careful about. Okay, Looking at more points from the executive summary, a combination of policies and mechanisms will be necessary to support CCS development and deployment. Carbon pricing can play an important role, but is not sufficient on its own. All these things have to be considered. In the early stages, the CCS initiatives are likely to require additional support in the form of top-ups such as contracts for difference that complement the carbon price and provide a higher and more predictable price signal. So this is about keeping the economy growing without slowing the economy down, without necessarily affecting consumption too much or per capita carbon footprint, but somehow bringing in CCS along with ETS to deal with the decarbonization pathways. Then looking at the economic gap in terms of carbon price versus cost of carbon capture. Here we are looking at 2008 to 2050. So we have been in the range of $600 per ton of CO2, and you can see here the range of observed emission trading system allowance prices have varied around these numbers here. So range of values observed in studies estimating and forecasting cost of CO2 capture here. Range of values for CO2 capture, that is excluding transportation and storage costs. Broadly speaking, direct air capture costs determine the upper end of the range, while fossil energy and industrial point source capture costs determine the lower end. So this is where you have difficult capture problems like direct air capture, and these are the point sources which determine the lower end of the prices. So where will it be good enough, and whether CCS will not be necessary for many industries because they will do a lot of point source capture or at source capture, so that the fuel they consume, they will make sure that the carbon is CO2 emissions from those fuels are captured at source before it reaches them, and so on and so forth. Policy makers must balance the numerous risks and trade-offs associated with the use of CCS applications when considering their role in decarbonization pathways. That seems obvious, and yet the main concerns related to CCS applications do include legitimizing business as usual, so continued consumption of fossil fuel activities, the underperformance of the technologies that exist, so nobody may want to move to a newer, more efficient technology with capital investment, alongside resulting doubts over its ability to deliver reductions and removals at scale, and of course generally concerns about the magnitude of carbon dioxide removal as a whole. Mechanics of ETS-CCS interactions inside and or outside ETS sectoral scope. There are many points considered. Again, I won't read all the details. ETSs can interact with CCS applications irrespective of whether the relevant sectors are covered by the ETS or not. So once the emission trading system is there, the CCS applications also will go on parallelly, and ETS may not directly cover some of the sectors, but indirectly it will interact with CCS as well. Okay, the ETSs in Germany and Austria, for example, exclusively cover emissions upstream. Okay, so this is something one has to keep in mind. Where are the ETSs being aimed at? Interactions with fossil energy and industrial point source capture are simplest in ETSs that regulate emissions at source. So that's the easier case to deal with policy-wise, implementation-wise, and just in terms of practical applications. Interactions with fossil energy and industrial point source capture are also possible for ETSs that cover emissions upstream. So ETSs with upstream coverage that wish to interact with the industrial point source capture could, for example, award a unit, for example an allowance or an offset credit, to entities performing capture from an industrial point source, which could then be sold in the ETS market. Alternatively, the ETS could allow certain entities, for example coal power plant, to voluntarily participate in the ETS. These entities would assume compliance obligations but also be incentivized to capture their emissions. So this is ETS and CCS working together. Interactions with technological removals within the ETS scope are possible, but the mechanics may vary by applications. So whether the emissions are considered not emitted at all because of CCS, or whether they are considered as emitted and still have to be under ETS, are details, because you have BECCS and waste to energy with CCS that could be covered directly under an ETS as proposed by some people. Such applications could, for example, be allowed to voluntarily participate in the ETS and receive free allowance allocations on the basis of renewable biomass used by the plant. Details, right? But they matter. Interactions with technological removals outside the ETS scope can be akin to offsetting provisions. So people emit some CO2 or greenhouse gases, then they pay someone else to offset it for them by planting trees or doing carbon removal elsewhere in some way. And with technological removals outside the ETS, the scope can be akin to offsetting provisions. So how the CO2 removed may not matter if it is interacting with ETS. ETSs and CCS, whether to interact and with what? ETSs can interact with none, either or both CCS applications, so at source or with technologies. In option A, you have no interactions between the two. In option B, you allow interaction with fossil fuel energy and industrial point source capture applications. And in option C, you have interactions with technological removals. We'll look at a figure in a minute to make that a bit clearer. In option D, you have interaction with fossil energy and industrial capture, as well as with technological removals. Okay, so here you are combining the previous options. Interactions between ETS and CCS applications increase the flexibility for regulated entities in meeting compliance obligations in terms of their emissions caps, but can also affect companies' abatement decisions. So if you have CCS, then they may not worry about upgrading their equipment or production processes or their energy use, etc., to reduce emissions, but instead rely on CCS to meet their compliance requirements or compliance obligations. So this is how the phase space would look then. 4 options for interactions between ETSs and CCS. In option A, emissions trading systems does not interact with the CCS applications. In option B, ETS interacts only with fossil energy and industrial point source capture, so then you can consider that as emission not happening. In option C, ETS interacts only with the technological removals. In option D, ETS interacts with both fossil energy and industrial point source capture, as well as with technology removals. We'll visit this again in a minute. Increasing the points of interaction between ETSs and CCS can ease concerns related to ETS market functioning and price discovery as the ETS cap approaches zero. So if everybody has met their obligations in some way, then how do you maintain the ETS market? So allowance prices for residual emissions are also likely to be high when you approach zero, for example. Interactions with technological removals can increase the number of players in ETS and supply of compliance units into the system, alleviating some of these market issues. Next, increasing the points of interaction between ETSs and CCS can further incentivize CCS development and deployment, but this is contingent on price differentials and on the availability of additional support. Okay, so this, how do you maintain the markets or the drive for continuing CCS and so on, and keeping the emissions on target? Systems may not fall clearly within any of these options that we have looked at. This could be the case when an ETS has no CCS specific provisions, but regulated entities could nevertheless reflect captured emissions in compliance obligations, notably through broader provisions related to the rules that determine compliance obligations and monitoring, reporting and verification requirements. So you can understand the technical difficulty. If you emit and capture, is it emission not counted at all, or do you have to count it and then be part of the reporting and verification process? So those are details that are important and yet challenging. ETS design considerations related to price dynamics and incentives for CCS applications are impacted by aspects of legal tender. So interactions with fossil energy and industrial point source capture inside the scope of the ETS relate to simply reducing the compliance obligations of regulated entities. But others, such as interacting with fossil energy and industrial point source capture outside the scope of the ETS, can entail awarding units to such activities. So whether you got credit for reducing emission or not will depend on how these interactions happen. To the extent that units or allowances or credits are allocated to entities involved in CCS applications, an important question is the relationship between such units and the emissions trading system cap. You can see that this will be a struggle all the way. If an ETS allows entities to reduce compliance obligations by capturing CO2, any free allocation of allowances could be affected by a reduction in reported emissions from entities capturing CO2. So somebody who's doing CCS can just say our emissions are low instead of saying we emitted but we took it out. So this will interact with ETS in a very different way. ETSs need strict and enforced criteria on what constitutes renewable biomass to ensure that environmental integrity of any biomass use in ETS. So if you have bioenergy with carbon capture and sequestration or waste to energy with carbon capture and sequestration, then it's a question of ensuring that additional carbon is taken out, so that bioenergy is actually initially taking out additional carbon and then sequestering it. So additionality is always very critical. The treatment of operational emissions and CO2 leaks from CCS value chain, capture, transport and storage within ETS must also be made clear. Coming to the ETS, which can be used as a tool to monitor operational emissions and CO2 leaks from the CCS value chain and provide economic incentives to reduce them. So whether these emissions fall under the scope of application of the ETS is regulated primarily through regulations on ETS scope and monitoring, reporting and verification. Excuse me. Liability provisions in case of CO2 leaks out of geological storage sites are necessary to ensure the environmental integrity of the use of CCS applications. This is critically true anyways, this independent of ETS. Only the EU ETS and the UK ETS currently explicitly include the entire CCS value chain within the ETS scope. So this is evolving, and different countries and continents are taking different approaches. Some ETS can reflect storage outside their jurisdictional borders, while others cannot. So you have CCS, then does it matter where you sequestered it? Within your jurisdictional borders or outside? So finally, brief considerations on CCU. CCU applications are widely and have CCU applications vary widely and have different environmental outcomes. We have discussed this elsewhere, so I won't go into the detail. Provisions related to the triggers for compliance obligations are important in determining whether an ETS interacts with CO2 that is captured and used in a product. So again, ETS has to worry about what happens to the captured carbon that's being utilized, which means it's still in the system and not sequestered out of the system. Depending on the provisions related to performance, monitoring, reporting, verification, and the ETS scope, reflecting CCU applications under ETS can lead to a shift in emissions out of the emissions trading system. So literally you have emissions that are happening and are not in the ETS system, and those that are in the ETS system. So you have to worry about the conditions under which the two are being accounted for. CCS and CCU relevant regulations within the current ETSs. Of the 26 ETSs currently in force, only 5 have regulations related to CCS or CCU applications. The EU ETS has detailed regulations for the use of CCS applications and is an example of a jurisdiction employing option B, where we had ETS and CCS interacting for the industrial and point sources. The UK ETS has incorporated several elements of the EU ETS and is an example of a jurisdiction employing option B. Okay. The Quebec cap and trade system contains some provisions that recognize the use of CCS and CCU and is an example of a jurisdiction employing option B. I'm not going into the details of these options, but just keep in mind the points that are being mentioned and the regions which are dealing with these options. The Net Zero ETS has operational provisions that are relevant for CCU. It also contains some CCS, but these are not, sorry, NZ here is New Zealand, not Net Zero. My fault. The New Zealand ETS has operational provisions that are relevant for CCU. It also contains some provisions on CCS, but these are not in force, and New Zealand is an example of jurisdiction under option A. So here the New Zealand ETS contains provisions for reducing compliance obligations by permanently embedding greenhouse gases in a product. So if you lock it into, let's say, cement or something else which comes under CCU, then you have some options of how it is counted in ETS. California Cap and Trade Program does not currently recognize CCS or CCU as a means for a covered facility to reduce its emissions and compliance obligations, nor does it have provisions for enabling technological removals. So it just eliminates CCS technological removals from the calculations under ETS. It therefore falls under option A. Okay, here we are. Interactions between selected ETSs and CCS applications. Here ETS does not interact with CCS applications at all in option A. So you have uncertain interactions between the ETS and CCS applications, and these occur in Austria, California, China, Germany, Kazakhstan, New Zealand, Oregon, Saitama, Switzerland, and Tokyo. In option B, ETS interacts only with fossil energy and industrial point source capture. So you have Korea, Massachusetts, Mexico, and the Regional Greenhouse Gas Initiative, which is a conglomeration of various states in the US. And you have option C and option D here. Okay. In conclusion, considerations on the interactions between ETSs and CCS or CCU are still in their infancy. Of the 26 ETSs in force, only 5 have any provision on CCS, only 2, the EU ETS and the UK ETS, have detailed provisions, and only 1 from Quebec has facilities that reduce compliance obligations through CCS applications. So any facility that is doing CCS has a lower burden on ETS. No empirical data on the interactions between ETSs and CCS is available, and many additional issues and questions are likely to arise as CCS projects materialize and jurisdictions engage with them. The fast pace of innovation and technological development presents a challenge for policymakers who may have to establish regulatory frameworks that can adapt to changing technological circumstances. Whether it's the success of DAC or failure of BECS, all these things have to quickly be converted into policy adjustments. However, as the pipeline of CCS projects grows, so will the pressure from stakeholders for clarification about the relationship between these projects and ETSs worldwide. Now is the time for jurisdictions to start grappling with these questions. So to look at the map of ETSs alongside intentions to make use of CCS and CCU applications, here are the regional, so this is the Regional Greenhouse Gas Initiative here. Washington, Oregon, California have banded together. Quebec, Nova Scotia up there, and EU and UK ETSs, Switzerland, and you have various ETSs under development or under consideration here in Colombia and Chile, in Thailand, Indonesia, Japan, and so on. And you also have China with and New Zealand playing already ETS in force. So stated national level intention to make use of CCS or CCU applications. So they will already be dealing with interactions between ETS and CCS or CCU. So it's a bit longish here, but that's okay. This is an important topic. So we know that emissions trading systems will be needed, or many are already in force, cap and trade, or so bottom up or top down or bottom up implementations of various emissions tradings, and you have CCS and CCU going on independently. So how they will interact, how they have to interact, and how policies have to manage these interactions are all big challenges that are discussed here. So it's okay that it's a bit longish. Okay.